Hello everyone. For today's video lecture, we're going to be talking about the principle of work and energy for rigid body systems. So the principle of work and energy is best summarized as this. The work done to a system will be equal to the change in the system's energy. If we put this all together in a single equation, we wind up with the following. So W, work, is equal to delta KE plus delta PE. We've broken up our energy into kinetic energy and potential energies, just like we did for particles. And we still have the same base equation, it's just the terms that we plug into this are going to be slightly different with a rigid body. So to start a work and energy problem, we usually need to start by defining an initial and final state. Energy happens at an instant, so we can define the kinetic energy and potential energy at any instant in time, whereas the work is going to occur between those two states. So if possible, we're going to draw these out and label relevant information at each step. So any velocities, any change in height, any distances that are important, we're going to label those in our diagram. So here we have an example of a diagram that I would use for like a barrel rolling down a hill. So we've got the initial state at the top. I've got the initial angular and translational velocity. Same thing at the bottom. I've got the final angular and translational velocity, and I've got my delta H labeled in there. So this would be a good starting point for my analysis. So after I write my diagram, the next step is going to be setting up the equation. So after defining our initial and final states, kind of drawing out our diagram, we want to determine all of the terms that are going to go into this. We want to determine the amount of work done, the kinetic energy at the start or initial or final state, potential energies at the initial or final state, and so on. So some of these values may be knowns that we can calculate based on given values. So if we know something starts from rest, like kinetic energy initial might be 0. If I know the velocity, I can do 1/2 mv squared. If I know the angular velocity, 1/2 I omega squared, etc. Some of these values might be unknowns that we're looking to solve for. So hopefully it is just 1. And some of these are terms that may not be relevant to the problem we're working on. So when you're working with a system that has no springs, for example, you may not have any elastic potential energy in your system. Same thing if there's no change in height, no change in gravitational potential energy, and so on. So all of these terms, we're going to plug them into our single equation, W equals delta KE plus delta PE. All right, so as a review from the previous section, here are the different terms that may go into our system. So for work, we have both translational, force times distance, or angular or rotational work, moment times delta theta. For our kinetic energies, we're going to have 1/2 mv squared for translational velocities. We're going to have 1/2 I omega squared for rotational velocities. So do be careful with this. So if we have just translation, we'd use just the top. If we have a fixed axis rotation, we'd use just the bottom. If we're using an instant center, we'd also just use the bottom. If we have general planar motion where we have translation and rotation, we're not using instant centers, we'd have both of these terms, so translation and rotation showing up in there. For gravitational potential energy, we still just have one term, mg delta H. Do make sure that the change in height, that delta H, is going to be the change in height of the center of mass of your body for these rigid body systems. And an increase in height is positive, a decrease in height is negative for that. And then finally, we have the elastic potential energy. This 1/2 K X is going to be used for linear springs, so springs that work by stretching or compressing them. And then 1/2 K theta is going to be for our torsional springs that we possibly have in the system. So generally, you're not going to have both of those kinds of things at once. Generally, you're going to have linear springs or torsional springs. Pick whatever is appropriate, if it's appropriate at all. So all of these terms will go into our equation. Whatever is relevant goes in there. Whatever is not relevant, you're going to leave out. And one of the primary limitations of this work and energy method, though, is it's only a single equation. I kind of brought this up already. So because we've only got a single equation to work with, we can only solve for a single unknown. So for this reason, we often need to supplement our one equation with other kinematic relationships. So if we are working with something like a barrel rolling down a hill like we had in that initial diagram. I might need to relate linear and angular velocities. For that, I would assume rolling without slipping, for example, for that. And I may also need to relate positions and displacements for potential energies. So the change in height, I might need to relate that to the stretch in the spring, and something like that. So figure out what it is that you can do. If you've got more than one unknown in your final equation, figure out what it is you can do to relate those unknowns to one another. And in that relationship, you can plug back into your equation, reduce it down to a single unknown, and solve. And that is the last step of this, is solve the equation for the unknown value, or equations for values if we have those kinematic relationships as well. With only a single equation, it should not be too difficult. These are not vector equations. These are just scalar values. However, a single equation can often get quite large, particularly with these rigid body problems where we have things like translational and rotational energy or kinetic energies. So simplifying the equation in steps may be useful. Often what I'll do is I'll draw out the enormous equation, plug everything in, figure out, the total translational kinetic energy is this many joules, the total rotational kinetic energy is this many joules, and so on, and kind of work my way down to a simpler equation where I can solve for the unknown that I need. So do pay attention to signs. Generally, we're going to increase some of those energies, so it's delta KE and delta PE. So figure out if KE is going up, KE is going down overall. And like I said, with gravitational potential, going up is positive, going down is going to be negative for that. All right, so that is the general process. We're going to talk about some other exceptions, or not exceptions, but some other extensions of this. So if we have a system of rigid bodies, so if, say, for example, we want to work with a couple of boxes that are connected, or like a cart, the same process can be applied to, that is applied to a single body, can be applied to a system of bodies. When the equation is applied to the system of bodies, though, remember that only external forces can do work on a system. So if it's an internal force, it doesn't do any work, because those terms are going to cancel each other out. So the example to the right over here, the moment, so we've got two boxes connected by a cable hanging over a pulley. If I turn this pulley, the moment exerted by that pulley is going to be work done to the system. But the tension in the cables, that is an internal force. So that would not be counted as work on the system. So sometimes by treating the whole thing as a system, we actually can simplify the process because we only have to worry about those external forces and moments on our system. I do have to worry about the kinetic and potential energies, and these can be lumped together, so I could figure out the entire mass and the entire velocity of the system, or I just add them up together. So I've got two boxes, I might have a kinetic energy initial and final for each of those, as well as a change in gravitational potential energy for each of those. Just add them all in piece by piece into your one equation. All right, so that's how we deal with systems of bodies with work and energy. The next, I want to talk about the conservation of energy. So in many cases, there's going to be no external forces acting on the body of interest. Of course, we don't include gravity or spring forces in this because those are counted with the potential energies. And in this case, there's no work done to our system. As a result, there's no change in overall energy in our system. So we might have something where, just say I'm dropping an apple off the side of the deck. In that case, there's no work because the only external force is gravity. In that case, I am losing gravitational potential energy and increasing kinetic energy. So very common to have these conservation of energy setups where the work is zero. And in this instance, we refer to it as conservation of energy, and some people refer to this whole thing as conservation of energy as well. So we use those the principle of work and energy and the conservation of energy, we use those semi-interchangeably in this book. And then with this, we can also rearrange the equation and just kind of put all the initial stuff on one side, initial kinetic and potential energy, and balance that with the final kinetic and potential energy on the other side. So other than the change in equations, though, the process for solving these problems is much the same. We don't have any, we still go through the diagram, we still go through setting up the figuring out the parts of the equation, plugging all those in, and solving. And as a review, the entire process with any of these work and energy problems, so set up your diagram, show any forces or moments that are acting between the two states, show any known or unknown velocities and angular velocities, identify the change in height if that's applicable, and identify any x or theta values for springs, that is the amount of stretch if applicable. Next, we're going to use the diagram to put together the single conservation of energy equation. So W equals delta KE plus delta PE, or alternatively, our conservation of energy equation we just talked about. And if we have more than one unknown in this equation, we need to come up with some additional equations, some kinematics, or just geometry relationships to relate those unknowns. And then finally, solve the equations for unknown quantities. All right, so that's all we've got for today's video lecture. Thank you for watching and hope to see you again.